whenever we are trying to interface an IO device, so these are the requirements. So, we have to identify the device through a port number. So, device should have an address and that address has to be generated either in a memory mapped fashion or an IO mapped fashion. So, whatever be the strategy. So, we have to somehow select that particular device and enable the device in a read and write control signal. So, if you are trying to make some input operation, then the read signal has to be given. If you are trying to do some output operation, then the write signal has to be given. So, read for input device and write for output device, and only one data line is used to transfer the information instead of the entire data bus. So, this serial IO. So, if you are doing a serial IO, then instead of doing that 8-bit data transfer, so we are doing only 1-bit data transfer, and that we will see that the rem and sim instructions, so they will be useful for this purpose. So, next. So, this the data transfer that we are talking about. So, this is microprocessor control. It can be microprocessor control, the unconditional. So, it may be that it is just microprocessor just transfers something to the IO device or reads something from the IO device, or it may be a polling, that is at periodic intervals. So, it transfers some data, or it may be some checking some status, etc., or it may be controlled by the device. So, device may give an interrupt. So, as I said that it is interrupt driven IO. So, device gives an interrupt to the processor telling that some data can be transferred now. Now, in case of synchronous data transmission, the transmitter and receiver, so they are synchronized with each other. A sequence of synchronization signals is sent before the communication begins, by which this the communication will be synchronized. So, they will be transferring at some clock rate. So, both transmitter and receiver, they should operate at the same clock rate for getting the values properly. So, there is a synchronization signal usually used for high speed transmission. So, more than 20 kilobits per second, and it is a message based transmission. So, synchronization occurs at the beginning of a long message. So, once it is synchronized, then only the actual transmission of data can start. On the other hand, this asynchronous data transmission, so transmission can occur at any time. So, that way it is better. So, you do not have that synchronization sequence to be done, and it is character based. So, every character is sent separately. So, there is a particular format for sending the characters, and those characters will be having those characters will be having some start bit, stop bit sort of thing, and then based on that the individual characters will be sent, and then generally they are used for low speed data transmission. So, less than 20 kilobits per second. So, in case of asynchronous data transmission, it follows agreed upon standard. So, there is some standard for the asynchronous data transmission. So, both the transmitter and the receiver, they must agree on the standard that it will follow. In terminology, in case the logic 0 is called the space, okay, that is the transmission, and logic 1 is called mark. So, this is very old terminology. So, that is followed. So, logic 1 is called mark and logic 0 is called space, and transmission begins with a start bit which is low. So, normally the line is high, and when the transmission starts, it sends a low start bit, and then 7 or 8 bits representing the character is transmitted. So, that is for ASCII is 7 bit, and some other code like EBCDIC, that is 8 bit. There is extended ASCII which is again 8 bit. So, anyway, so that 7 bit or 8 bit will be transmitted. So, that is D0 to D7, those bits are transmitted, and the transmission is concluded with 1 or 2 stop bits. So, after that 1 or 2 stop bits are transmitted after 7 bits, after 7 or 8 bits have been transmitted as per the protocol. So, 1 or 2 stop bits will be sent to tell that okay, this is this particular character transmission is done. Now, as far as the transmission policy is concerned, it can be a simplex transmission. So, only one way transmission. So, the transmission is always from the master device to the slave device. Like if we are thinking of a system where microprocessor is connected to a number of devices, and all these devices may be output device, and then the processor always transfers to the device. On the other hand, if the input device, then the device, the processor always reads from the input. So, that way it is like a simplex transmission, the one way transmission. So, only one wire is needed to connect the two devices, because it is only one way transfer. So, communication from computer to a printer. So, in most of the cases this is simplex, excepting the situation that sometimes the printer status has to be told and that comes as a message from the printer. So, for those type, excepting those type of cases, so it is a simplex communication. Then we have got half duplex communication. So, two-way transmission, but only one way at a time. So, it is a communication between the transmitter and receiver, but at one or the sender and the receiver, but at one point of time the transmission is in only one direction. So, basically the telephone conversation, so they are of half duplex nature. So, again one wire is sufficient because at one point of time the communication is going only in one direction. But the problem with simplex and half duplex is that the speed of transmission is low because we cannot communicate both ways simultaneously. So, the full duplex is a situation where the data can flow in both the ways at the same time. So, two wires are needed. So, like transmission between two computers. So, they transmit between themselves simultaneously. So, that is the full duplex type of communication. As far as the rate of transmission is concerned, for parallel transmission all of the bits are sent at once, okay. So, because parallelly all the 8 or 10 bits can go, but for serial transmission the bits are sent one at a time. So, one bit at a time. So, therefore, there needs to be an agreement on how long each bit stays on the line. So, before starting the transmission, the sender and receiver they must agree about the bit duration, the duration for which the bit should be lying onto the line. So, that is the so how long it should be there in the line. The rate of transmission is usually measured in bits per second, also known as baud. So, which is actually symbols per second, baud is actually symbols per second, but many a times we just use it for the sake of simplicity bits per second also, but baud is actually symbols per second. Now, how can you determine length of each bit? Given a certain baud rate, how long should each bit last? So, that is the baud rate. So, if I take baud as bits per second and second per, so if I just if I divide the other way, seconds per bits equal to 1 upon baud. So, at 1200 baud, okay, so a bit will last 1 by 1200, that is 0.83 millisecond. So, each bit from the start of communication from every bit will be 0.83 millisecond. So, that is how the bit duration is determined. Now, for transmitting a character, so to send the character over a serial communication line at a baud rate of 56.6 kilobit per second, okay, the baud rate of 56.6 kilo. So, the ASCII for A is 41 hex, that is this is the bit pattern. Okay. So, we must add one start bit and two stop bits. So, this is the start bit. Okay. So, that is so first we start transmitting from the LSB side. So, first the start bit will go, then the 7 bit 8 bits will go, and then finally 2 stop bits. Now, each bit should be 1 by 56.6 k, that is 17.66 microsecond. So, this is also known as the bit time. So, after transmitting a character, we should wait for 17.66 microsecond, and then only we should transfer the next bit. So, we have to set up a delay loop of 17.66 microsecond and set the transmission line to the different bits for the duration of the loop. So, that has to be done. So, this program can be written very easily. So, we can do some serial transmission and then wait on a loop for 17.66 microsecond and then transmit the next character, next bit. Now, in the process some error may creep in, like say it is transmitted over a signal line. So, that signal line may get some error. So, that how to get rid of those errors. So, we have to at least check for the error, and we need to if we need to correct it, some additional information has to be transmitted for the correction, at least for checking also it has to be transmitted. Now, for error checking techniques, so there are well known techniques like parity checking and checksum. So, these techniques are for error checking and not for correction. They just check whether the received bit pattern that it has got, so whether it is possibly correct or not. And then if there is an error, then in many cases, so it can detect that situation that an error has occurred, and it can tell the transmitter that okay, there was a problem with the last transmission, so that the transmission can may be repeated by the transmitter. However, any such error checking technique, it cannot guarantee that all possible errors will be caught. At the same time, it cannot indicate whether where or what the correct information is. Okay, so what is the error or what is the correct information? So that it cannot check, but it cannot tell, but many a times it can detect the situation that an error has occurred in the transmission. So as far as the parity checking is concerned, so maybe while transmitting the data bits, so we make the number of ones in the data odd or even. So if the ASCII is 7-bit code, so bit D of the parity information. So if the ASCII code is a 7-bit code, so we can have another bit can be added for the parity information. For the even parity, the transmitter will count the number of ones in the data. If there is an odd number, then this D bit will be set to 1 and make the total number of ones even, and the receiver will now calculate the parity of the received message, and it should match the bit D. Okay. So if it does not match, that means there was some error in the transmission. So that is how this parity checking works. Other possibility is using checksum. So parity works at the individual character level, because otherwise what will happen is that it will not have that much capability to determine all the errors. Okay. So that way because if there are so more than one bit failure, so these parity bits check may fail. Okay. So that may say that the data is the data has been received correctly, whereas there are multiple failures for which it is not detected by that mechanism. So if you have got larger block of data, then this checksum is useful. So the transmitter adds all of the bytes in the message without carries, and then calculates the 2's complement of the result and send that as the last byte. So suppose a transmission is spanning over say 100 bytes. What the transmitter will do, it will just go on adding those 100 bytes, and then at the end it will take so the carries will be discarded, and at the end it will calculate the 2's complement of the result, and the result will be sent as the last byte. So at the receiving end, so it will again calculate all the sum out all the messages including the last byte, and since I have taken the 2's complement there, so if I add this, the result should be 0, because that is the negative number. So now the result should become 0. So the receiver can simply check whether the sum of all these bytes received along with the last byte is 0 or not. So that way this checksum can be used. One standard for the communication, so serial communication, is RS-232 standard. So is a communication standard for connecting computers to printers, modem, etc. The most common communication standard is existing till 1950s. Since 1950s, it uses voltage levels between plus 15 volt and minus 15 volt. So minus 15 volt is taken as logic high, plus 15 volt is taken as logic low, and it is restricted to speeds less than 20 kilobaud. So the speed is low. Restricted distance is within 50 feet or 15 meter. So distance is also restricted. The original standard, it uses 25 wires to connect the two devices. However, in reality only 3 of these wires are needed. So original standard was 25 wires, but since the distance is not that much, so now often 3 wires are sufficient. Now if we are using some microprocessor for transmitting this data serially, so we can use some software control mechanism for this serial transmission. So what are the main steps involved in this transmission of a character? The transmission line is at logic 1 by default, so that is high. So first we have to transmit a start bit for one complete bit length. So for one bit length, so it should transmit a 0, which is the start bit. Then it will transmit the character as a stream of bits with appropriate delay. So it will start transmitting the character bits one by one. So 7 bits will be transmitted. Then it will calculate the parity and transmit it if needed. So it will calculate the parity, and the parity if it is has to be 0 or 1. So based on that it will be sent, and then it will transmit appropriate number of stop bits, and then the transmission line should return to logic 1. So this is the flow of any software routine. So that will be responsible for doing the serial transmission. So suppose I have got a microprocessor where in the this bit D0 is actually doing this is having the bit pattern, and that is from D0. So, it is connected to the output port and that is going to the serial output. Now, if you are transmitting this pattern, then first it will be giving the start pulse which is low, then this 1 will go, then all these zeros will go, then 1, then 0. So, all these bits, so they will be shifted one by one and they will be transmitted over from this bit D0 onto the outside world serially, and finally 2 stop bits will be transmitted. Okay, so, on this line D0. So, over the time, so this happens like this: first start bit, then this 1 0 0 0 0, then 1 0, then 2 stop bits. So, that should be the mechanism. So, how we should do the serial transmission? First we should set up bit counter. So, set up bit counter, so that is actually setting the for the bit delay. So, how much delay should be there? So, that is determined by this bit counter, that depends on the baud rate that we have we are going to process, we are going to have in our system. So, it will set up the bit counter and set bit D0 of A to 0 to generate a start bit. Then we wait for a bit time. So, so that way that 0 is transmitted over this from this D0 of the accumulator for that much time. Then we get the character into the accumulator, wait for a bit time, rotate a left. Okay, so, we rotate a left, so that is basically a shifting, and decrement the bit counter. So, we just so how many bits will be there? So, those bits will be transmitted. So, till it is last bit, so it will be going on doing this operation, and then it will wait for the bit time. So, how much time it has to wait? So, it will wait for that. So, this way it will be going on. So, this bit counter actually is setting how many bits the data will have. So, there is so many times the bits will be transmitted serially, and between every 2 bit transmission. So, we are waiting for this bit time which is fixed by the baud rate, and then after the last bit has been transmitted. So, we will send the parity bit and we will send the stop bits. So, they are not shown here very clearly, because again there will be bit times between this parity bit and stop bits to the 2 stop bits and all. So, they with the bit timing information will be there, it is not shown here explicitly. On the receiving side, the main steps involved in serial reception is that wait for a low to appear on the transmission line. So, transmission line is generally high. So, the start when the transmitter starts sending the signal, so it will be making it low. So, that way it will be making the transmission line low. So, the receiver should wait for the start bit. It should read the value of the line over the next 8 bit length. So, that is the 8 bits characters will be there. So, it will read the 8 bit lines 8 bit values. Then it will calculate the parity and compare it to the to bit 8 of the character to see whether the parity has been received correctly or not. And if the parity bit checking is being used, then only this step will be done, and verify reception of the appropriate number of stop bits, that is 1 stop bit or 2 stop bit, that depends on the standard that we are following. So, based on that it will be getting the appropriate number of stop bits. So, it should get those bits. So, for transmission, for the reception, so it is from the input port. So, this D7, the bit D7 is actually getting the input, the serial input in case of 8085 processor. Now, it should get in this sequence. First it should get a start signal. So, previously the line was high. When it gets the start signal, it will know that now the serial transmission is going to start. Then this so this 0 1, then 0 0 0 0 1, then so this is the parity bit. So, since this is following an even parity, and the bit this byte that we have sent, already 2 1s are there. So, this parity bit is equal to 0, and then it will expect that 2 stop bits will be transmitted. So, all these should come onto the line D7. So, if they are received in this sequence, that means the character has been received correctly over the serial transmission. So, the flowchart for the reception process is like this, that it will read the input port. So, as long as there is no start bit detected, so no action. So, it will just go on reading the input port. If a start bit has been detected, it will wait for half bit time, and bit is still low, then it will if bit is high, that means there was a glitch. Okay. So, that part that has to be ignored. So, if there is a glitch, the bit is not low, that means there is a glitch. So, it goes back to check the start bit again, and if it is bit is still low, that means it is not a glitch. So, it will start the bit counter, it will wait for the bit time. So, how much time it has to wait for a bit, so that it will wait for that much time, and then it will read the input port, it will decrement the counter. So, that the last bit is so that way it will go on. So, till whatever be the number of bits that it wants to, that it expects to receive. So, based on that, this bit counter will has been set. So, so it will be decrementing that counter, and when all those bits have been received, then it will be it will come to the check parity and wait for the stop bit. So, it will again, this part is not written thoroughly. So, this is again waiting for two contiguous 1 bits for the stop bit. So, that way this whole operation take place. So, this is the flow chart for the serial reception part. So, in case of 8085 processor, so it has got two serial pins, SOD serial output data and SID serial input data. So, serial input and output is controlled using the RIM and SIM instructions that we have in 8085. So, just to recapitulate, the SIM is so it has got these bits 7. So, this accumulator bit 7 gets the so whatever be the value there. So, serial data output, and this SDE serial data enable. So, if the serial data enable is equal to 1, then whatever is the value available in the SDO, that is bit number 7, will be put onto the serial output data, okay, in the SIM instruction. Similarly, we have got for the serial input the RIM instruction. So, RIM instruction, so here this serial data input, that is coming, that pin value will be coming to SID pin. So, that pin value will be coming to bit number 7 of the accumulator, which is the serial data input, and here of course, there is nothing like enable and all. So, this is the RIM and SIM instruction that we have seen previously for doing this serial output and input. So, using this SOD and SID pins, the user would not need to bother about setting up input and output ports, because they are only single line output is a single line connection is there, and these two pins themselves can be considered as ports. So, you can connect it to some other device that supports this serial transmission, and then it can go like this. The instructions SIM and RIM are similar to the out and in instruction, except that they only deal with 1 bit serial output data and serial input data ports. So, we can think of this SIM and RIM as if they are equivalent to 1 bit operation. So, this is an example to transmit an ASCII character stored in register B using the SOD line. So, first we set up like how many bits we want to transfer. So, there is the 8 bit of ASCII data, plus we will be transmitting one start bit and 2 stop bits. So, total 11 bits we want to transmit. So, in the C register we note down the counter for 11 bits. So, MVI C comma 11. So, that will have this 11 bits count, that is the count 11. Then XRA A, so it will clear the carry flag, and then MVI A comma 80 hex. So, that is setting the D7 equal to 1, and then this RAR. So, this will bring carry to D7 and set D6 to 1. So, this is actually rotate accumulator right. So, they rotate right. So, the bit D7 is since the carry was reset previously. So, by doing this rotate, so we will get the carry bit coming, the 0 bit from the carry coming to D7, and the bit numbers D7 was set to 1 previously. So, that goes to D6. So, that now the SIM instruction. So, in the SIM instruction, if you see in the SIM instruction, so we have got this SDE pin, SDE bit has to be 1 for transmitting that. So, for sending the start bit, so this SDO bit should be 0 and the SDA should be 1. So, that is exactly what has happened here. You see that after doing this, so this bit D6 has become equal to 1. So, SDE is equal to 1 and bit D7 is equal to 0. So, that is why it is transmitting the start bit. So, this SIM will transmit the start bit. Then we have to wait for the bit time. So, this call bit time. So, this makes this is a delay routine. So, it is not written here explicitly, but you can understand that it will be calling the it will be the delay routine for that 1 bit time. Now we want to transfer the characters. Okay. So, STC, so that it will set carry to 1 and move A comma B. So, that will place the character in A. Now we do a rotate right. So, as a result this shift D0. So, the character to the carry, so D0 of the character to the carry. So, D0 will come to the to the carry bit and 1 will come to the D7. Then we save this intermediary value, intermediary character that we have in B register, then decrement C and JNZ next bit. So, next bit will be getting again this carry as D7 as 1 and then it will be doing a sim. So, let us take a pattern, I think. So, I think we can take a pattern and try to understand that how it is working. Suppose I said that in the B register I will have the bit pattern to be transmitted. Suppose I have the bit pattern 1101 0100. So, this is the bit pattern to be transmitted. So, up to this much from the beginning we have seen that we have transmitted the start bit. So, up to this much is okay, and then what we are doing? So, we are setting the carry bit to 1. So, this is the carry. So, carry is set to 1 and move A comma B. So, A register also gets 1101 0100. After that there is a shifting rotate accumulator right. So, as a result, so D0 will be coming to the carry. So, this carry gets this D0. So, this 0 comes here and shift 1 bit to 1 into bit D7. So, this since carry was previously set to 1. So, this 1 will be coming to D7. So, this all these things are shifted. So, this 0 goes here, 1 comes here, then 0 1 0 1 sorry. So, this all these bits will be shifted. So, I will get 1 1 0 1 0 1 0 and then this 1 from the carry. So, it comes here, okay, by this rotate right instruction. So, it will be D0 bit D0 of this accumulator will be coming to the carry and this carry which was set to 1. So, that will come to the bit D7. Then this result, this intermediary result is saving on to the B register. So, B has got this particular value, then decrement C. So, C we have 1 bit is decremented and jump on not 0 to next bit. So, it will be coming here, then it will be moving A the 80 hex. So, this 80 is having this A register will have this 80 pattern. This is the A register and then rotate right. So, this 1 will be coming to this position and this carry. So, which was set to which was having the value 0, which is the LSB pattern that we have. Okay, that LSB will be coming to this position. Now, after that when I am doing a sim, actually this 0 will be transmitted, which is nothing but the LSB of the character. So, this character is now this bit is now transmitted. In the next stage, since the B register has got this value. So, 10 has been already been transmitted. Next this 0 is there in the B register. So, this 0 will be transmitted, which corresponds to the 0 that we have at the next position. So, this way serially the bits will be transmitted one by one through the SOD line using this sim instruction and all.